Hello and welcome. Today we are talking about a data structure. This is my favorite data structure known as a trie. I think it's really cool because it allows you to store a lot of information in a really tight spot. But what is a trie? It is a kind of graph data structure, so it uses nodes and it allows you to basically connect bits of information in a sequence. So let's say, for example, you have the word R, A-R-E. And so you have a bunch of nodes stemming off of that, one node connected to the other in a pretty nice straight line. But then you could also have the word an, A-N, and you're basically reusing the A node. And so you can kind of have a lot of these strings all compacted together in a very tight spot. So today we're going to actually go over the implementation of this using Python. Then what we're going to do is we're going to take a whole dictionary, a whole lot of words, and we're going to just jam it into a trie, and we'll see how that works. I'll be covering a very basic implementation. I'll also go over some possible modifications you might want to do. And then I'll also showcase one modification that I think makes sense with a particular use case. So let's get into it. I want to first cover the test cases so that we know how this thing is supposed to work. So here I'm going to have my first test say that I can add words and check if the word is in the trie. So here I'm instantiating the trie. This is what it would look like. If I had the code working, this is what it would look like. The trie is here. We're going to add a word hello, and then I'm going to check to see is hello in the trie. So this should return true. And if I check for the word nothing, nothing should not be in the trie. And I'll print test pass if it all passes. If you get past these two without an error, assertion error, then you're done. For test 2, I'm just going to make sure that it has a count. This is kind of my own implementation. You can do all kinds of different things with this. But this, I'm going to instantiate it. I'm going to add the word hello. And then I'm going to check to see that the trie count is set to 1. Then I'm going to add another word testing. And that count will be now 2. But if I add the same word again, the count should not increase because it already exists in the trie. It shouldn't add it again. So that's how the trie is supposed to work from my perspective. And let's look at the implementation. So as with most graph structures, we're going to have a basic node class. So when this node is instantiated, I'm going to pass in a character, which that node will represent, which is stored internally. And then I'm going to check to see if this is an end node. So a lot of times you're going to need to keep track of like what is an end. There are a few ways of doing this, but to go back to my example here. So with the word R, A-R-E, there's like an end node here to recognize that this is like the end of the word. But you can have the word A-N, and you can kind of see how that's like its own end node. So I wanted to implement this in a way that was a little bit easier. So I'm going to actually just have the node keep that information, whether it's an end node or not. And that this will be true if it is. Here, I'm going to create the children for this particular node. I'm going to set it as a dictionary. This is just to have a quick lookup because I want to be able to pass in a character and quickly know, is this character a child or not? And be able to kind of grab the node that's associated with that as the value for that key. All right, let's run that and make sure that's locked in. Next is the trie itself. So there's a bunch of code here, but for the most part, it's not that crazy. So let's get into this. When a trie is instantiated, we will set the count internally to 0, meaning it has 0 words to start off with. And we're going to create a root node, and we're passing in the value none because it's not really doing anything. It's just basically housing all the children to start off with. Here, my rep R, this is literally just to have a representation. So I'm going to just try this out for real quick and show you what this looks like. So if I have a trie, and it just basically spits this out. That's what it's doing. It's basically showing the representation for that. If I did not have this, delete that, it would look like this, which is just a reference to where it is in memory. That's not so pretty, so I like to have a little rep R to showcase that it actually is a trie, has this many words. Whatever information I want, I could pass in to this string. It needs to return a string. So let's look at one of the main functions here, the main methods, I should say, where it's called add word. We're going to pass in a word, and we're going to be constructing all the nodes that are necessary for that. So I'm going to start out with the root node as the current node. And then for each character in the word, I'm going to find or create the child node. Let's check out what this find or create child node method looks like. And that's what it is right here. And it's going to take a node and a character. The character is basically like the child character that we're looking for. And here we are going to check to see if that character is in the node's children dictionary. If it is, then it's already been created. We can just get it and return it, and we're done. We are essentially finding the child. It already exists. If it doesn't exist, then we have to create it. And so that's what we're doing here. We're instantiating a new node with the character. And once we have that child node, we're going to add it to the children dictionary for that given node. And we're setting it there. And then we can return that child node. So either we find it or we create it, hence the name. Once we have that child node, we are going to reassign the current node to that child and then get the next character in the word. And then once we're done with all of that, we will essentially have the last character in the word. And what we can then do is check to see if the current node, if it's an end node. And if it is already an end node, then we don't need to do anything because we've essentially added a word that already exists. So that's why I'm doing this check here. We don't want duplicates to kind of add to the count. But if it's currently not an end node, essentially it's a new node that has not been considered an end before, then we will set that node is end Boolean to true. And then we can also increase our count on the try itself. So that's the main functionality. There's another one here that I'm going to talk about real quick called contains. And you'll notice that it has these 2 underscores. This is what's called a dunder in Python. This basically allows you to use the in keyword in Python. So if you have a string like hello, you can check to see if there's a character in that string. So you can say, is A in this? And it will return a Boolean true or false. This ability to say in is what contains allows you to do. So you'll notice that if you have hello, you can also do dot contains and then say A, and this gives you the exact same thing. So that's the idea. So we are going to use this to get the functionality that our test is asking us to do, which is here. It's basically allowing us to do that. All right, so what does that method look like? We're going to give it a word, and we're basically saying, does this word exist in the try? So how do we do that? We're going to pass in the word. So we're going to establish the current node as the root node. And then basically we're just going to go for each character in the word. And if the character is not in the current node's children, then we know that we can just stop short essentially and say return false. Otherwise, the character is found and we can just grab that character node and then continue down the chain. Once we're done with this word and we got through without missing a beat, then we know, okay, this character node, that's the last character. So here we are then at the last node in the word. We need to check to see if it's an end node. If it is not an end node, that means that this word is basically giving a partial match. So we're going to return is end true or false. So I'm going to instantiate that. Just to kind of showcase what this looks like, we're going to have our try, which I need to spell properly, like that. We're going to maybe add a word. Hello. So I didn't take casing into account here, but you might want to consider that. So okay, we add the word and we can check to see is hello lowercase in the try. It's going to say false, but if I put the capital H, it'll say true. And that's kind of how this thing is working. So let's go to the test. All right, so this first test is to check to see if we add a word, and we can check to see if it's in the try or not. And it should return true if it is and false if it's not. And that's what we're testing here. It looks like we passed the test there. Last test here is to make sure the count is working. Adding one word will make it a count of 1. Adding another will make it 2, but adding the same word will not change the count. Let's see if that works. And that looks like it's working as expected. Okay, so all those tests pass, but how do we use this thing in the real world? What I'm going to showcase here is a quick dictionary lookup. I have here a source that showcases a bunch of words, and let's look at the raw of that. These are a bunch of English words, and I think it's like over 300,000 or something. It's a lot of words, and you can see it here. So what we're going to do here is we're going to take that file, which is stored, I put it in this repo, which I will share, by the way, definitely in the description. You can see that. We're going to take that file, open it, and then read the lines into our try. We're going to add each word one at a time, essentially. So let's run that and see what happens. Okay, it didn't take very long, actually. So kind of speaks to the fact that this thing is pretty efficient. Let's see the try count. 370,000 words are in our try right now. And we can check and use it just like we would expect. Like the word hello should probably be in there, I assume. But some gobbledygook like that should be false. So we can see here that we have extremely quick lookup. So it's very similar to a set or a dictionary. And there is actually some other implementation that we can add to make this a little bit better. So let's check out some use cases. So some possible use cases for the try data structure. Well, for one, it's definitely optimized for lookup. So that's really good. We can also do some quick searches. So you can imagine this being something that users would find very useful. Like, hey, are these string of characters in this collection? So it's similar to a set. You can argue that it's actually more efficient than a set because it actually stores the entire word individually, each word individually. Whereas we're not doing that. We're being really efficient with the characters that we're storing. We're essentially reusing all the work we've already done in terms of like the node structure. What we could also use this for, and I mentioned this before, is partial searches. So you can't really do that with a dictionary or a set. If you want to see if the beginning of a word exists, you can't do that in those data structures. So you can actually see whether those characters exist in the trie or not. And if you wanted to, you can actually add some functionality to even keep the count of all the words that happen at each point after that node as well. So that's something to keep in mind. So you can actually modify what we've already worked on to be specialized for that particular use case. What's cool is that we do have deduplication, which is possible. So it's very similar to a set in that way. And you could even use it to serve as a even more efficient dictionary, because you can have key value pairings. So I didn't mention this before, but because you have that node, each node stores some information. You can imagine that once you get to an end node, you have some value that you're storing. Of course, we would need to add some functionality for that. So using this basic implementation that we just talked about, you can do a lot with it. So I'm going to actually implement one use case. I'm going to use a quick search, and I'm going to implement that, and we can see what that looks like. So here's the scenario. We have a book application. So you can imagine that users would want to search for a word in a large text. And we want to know how often those words show up, and also where are they located. So I want to kind of get an index. So these are kind of valuable things that you might imagine that a user would really find valuable, but being able to quickly have the search and quickly find out where those keywords are within the entire large text would often take a very long time, because you would need to scan through the whole document every time the user searches for the word. That would be very inefficient. I'm going to implement something called a WordSearchTrie, and we'll see what this looks like. Here are the modifications we're going to do. We're going to need to store the index location for each word in the end node. So once we get to the end, we know we need to store some information. So this is similar to up here, where I mentioned that we have kind of an efficient dictionary with key value pairings. That's what we're talking about. The thing I'm storing are the indices for where those words are in the text. So we can also get the count for how often this word shows up just based on how long this list is that we're talking about. All right, so let's check out the test and see how this is supposed to work. So our first test is going to be that we can add words and check if the word is in the trie. So very similar to what we had before. And it should return the indices for each word. So here we have our trie. I'm going to call it the WordSearchTrie. So we instantiate it. We're going to add a word. And notice that when we add a word, we're using the string, but we're also adding essentially the index for where that string is supposed to be in our text. And we should see that when we add to the trie, and look at this, this is a bit of a different functionality. Before we had the dunder contains, but here we're going to actually use a different dunder method, which is used for this kind of like key lookup. We're going to check to see if the word is in the trie in this way. And once we have this key, we're going to get the value, which is supposed to be a list of indices. So we added 0 as one of the locations for the word one, and we should get a list that has 0 in it. If we look for the word nothing, which doesn't exist in our trie, then we should get an empty list essentially. Basically, this word does not exist in the text that we're looking at. Next thing is duplicates are handled as expected. So in this case, we're searching for words and each word is being added to the trie. The duplicates are essentially okay to add because we do want to capture those. Those will have different indices. So here we have the addition of the word one with index 0, but we're adding one again at index 8. So when we actually look up to see where one is, we should get a list of 0 and 8. So that's what it's going to look like. Let's look at implementation. Okay, so just to give it a different name, I'm calling this node a word search node, but it looks very similar to the last one. We have a character that we're instantiating with. We're checking to see if it's an end. We're going to keep its children. But most notably, we're going to have a reference to indices because it's going to be a list. And this is specifically for end nodes. So this should really only show up for end nodes. All right, let's instantiate that and go to the next block here, which is the WordSearchTrie. So this thing, if you look at it, it doesn't look very different from our last one. We're going to instantiate our trie with nothing. We're going to have a count. We're going to have that as 0. We're going to create a root, which is our word search node with none, just like we did before. Very similarly, we're going to have the representation be kind of the same thing. And now we have the main workhorse for our trie, the add word, which is different now because we're going to have both a word and an index that we are considering when we add a word. We're going to start with the root node as our current node. And just like we did before, for each character in the word, we're going to find or create a child node. So this, and I don't think this is very different I think the only thing I really changed is the reference to the node when we instantiate a new node, but that's basically it. Everything is the same here. So we're going to loop through each character in the word, and the last current node that we have is the last character in the word, and that node we can then add to our indices. So this index should be unique. I'm going to assume that that is the case. So just like we did before, when we get to the end, we see, is this current node an end node? Because if it isn't, then we can set it to true, that it is an end node, and we will increase our count. And remember, the count is on the trie itself, how many unique words are on the trie. And then we have this, which is not very different. And then we have our new dunder method here, which you may not be very familiar with. It's called getItem. So whenever you use a dictionary and you have like a square bracket and you put a key, that's what you're doing. You're basically calling getItem. So if I check here, let me see if I can, so I'm going to instantiate this. I'm going to create a trie here called the WordSearchTrie. And then I'm going to add a word, call it hello. Hello, let's call hello. And we'll give it the 9999 for that. When we say WS_trie, and we can then put in brackets hello, we will get the list of indices. But this is the method that known as getItem. It's the same thing that we just did. It will return the exact same thing. So that's a kind of cool thing to know in Python. But anyway, so when we do getItem, we're going to be passing in the word, which is essentially the key that we're looking for. And we do similar to what we did before. We're going to grab the current node as the root node, and then we're going to look for each character in the word. If we don't find a character, then we know that this word does not exist in our trie, and we're going to return an empty list. Otherwise it does, and we're just going to get the next child. And then once we get that child, we're going to return the indices there. Now what's interesting here, now that I think about my implementation, and this is a good thing I'm realizing now, I did not check like I did last time about whether this is an end node or not. If it's not an end node, then we're basically looking at a partial. So for example, if I have this, I'm going to go back to my old square bracket. That's what I'm so used to. So if I have hello, but if I have hal, that's going to be considered valid as well. I guess it's not that bad because only end nodes, because this thing here will be empty, right? Because it'll be like not an end node. And so only end nodes will have this. So actually, I think it's okay. I'm going to keep this implementation. I think it's simple enough. So I'm going to keep it as is. Anyway, what I'm doing here is grabbing the indices, and I'm going to be returning a shallow copy of that. What this is going to do is recreate the entire list, but it's going to be a copy of the original. Why do I want that? Well, the idea is just as a kind of security thing, where if I put hello, and if I was returning this as a list, I could actually store this as a list here and then do like modifications to it, which you would definitely not want, you know. And then if I look at L, it would be changed. But if I look at hello on the trie, that should not be changed, right? So I do not want there to be any reference, because it's an object reference. I don't want anyone to modify it. That's all I'm trying to say. Okay, so that's our implementation. Let's see if our test passed. So this is test one. We can add a word and should return only the indices, and that passed. Very good. Here we're checking to see if we can handle duplicates. We should get a more than one index. So let's try that. And that test passed. Okay, so now we have a functional word search trie. How do we use it? How does this even make sense? Here I have another reference to some text here. This is a awesome website actually for large bodies of text. This is a book, Alice's Adventures in Wonderland by Lewis Carroll. So you can get it for free here. This is the Project Gutenberg. So definitely check it out if you are looking for large bodies of text for any of your word processing needs. And what I'm doing here is I'm going to first create a kind of pre-processing. Each word may have like weird characters or stuff. So I'm using this function to just substitute any non-letters to nothing, basically. So I'm removing non-letters. And you can see here I have like a bunch of characters here, and I have some lowercase, uppercase. I'm going to lower everything and remove any non-letter characters. That's the idea. So this function is going to help me with processing all the keys or the words from this large body of text. So here I'm going to load the book just to kind of showcase what this looks like. I have our file. Again, this is all in the repo, so you can check that out. And here I'm going to load and read in the first 1,000 characters. Again, just as an example for you all. So here I'm going to have my full text. I guess it's not really a full text. And that's what I'm creating a variable. And it is literally just going to be a string. Then I'm going to create a list of processed words. I'm going to note some stop characters, and that'll be useful when we're splitting things. Here, I'm going to get the max n, which is how long our text is, the length of the text, basically. So I'm going to be using this to basically, on my own, parse out this string, because I'm going to have like basically cursors. So here I have like the index cursor, or like the lagging cursor, and here's the fast cursor. So basically I'm going to be moving one ahead until I get to a stop character, and then I'll say, hey, that's a word. That between these two indices, that's a word. You need to parse that and then add it to our try. Or in this case, I'm going to add it to our list called process words, again, just as an example for you all. That's what I'm doing here. I'm checking to see if the cursor is less than the max n, because once we get to the end, we don't need to keep going. So while that is true, I'm going to then do some parsing. And so I'm going to check to see, again, ensuring that we don't go past the max n. We're going to check to see if the character in our full text, and again, this is a cursor, so it's just an index, if that character is not a stop character, because a space, I consider that these are essentially like the end of a word. Is it a space or is it like a new line? Because if that's the case, then we can stop. Once we do, we have now positioned the fast cursor up to that point, and then we're going to grab that word out of the full text between the index cursor and the fast cursor. That is our word. We're going to then process the word like we mentioned, and we will now have a processed word. If processed word is a thing, you might consider that maybe there is like a number that got reduced to just an empty string, in which case that's not really a word. So I'm checking to see, is this really a word? If it is, we're going to append both the processed word as well as the index cursor. And the index cursor is like basically where the word starts. So once we're done with that, we can then put our fast cursor one more. We want to get past the stop character. And then we're going to also set our index cursor to where that is, but essentially like resetting everything to like the next starting. And then we're just going to keep doing that until we get to the end of the text. I'll be returning our process words here. So let's look at this, what the first 1,000 characters look like. All right, and here we go. And you can see here that, well, we have the Project Gutenberg ebook. So this is not the full, I'm including some stuff that's not Alice in Wonderland, but it's fine. This is just a proof of concept. And you can see here that we have the word itself and the index that it starts out as. So 0, 5, 13. So this is what we're going to be basically putting into our try. All right, so now that we know what is going on with that, let's actually load our book into our WordSearchTrie. Everything is basically the same here. I now have my try here. Instead of only the first 1,000 characters, I'm going to read in the entire text, very large text. I'm doing the exact same functionality here, except when we get a processed word, I'm now adding the word and the cursor, the index cursor. I'm calling it the slow cursor here. I guess I should call it index cursor. Run that. And it's done already. Look how fast that was. My goodness. So we're going to check to see the word glass. How often does the word glass show up? Well, there we go. We have, well, remember, we don't have the count, right? We need to get the length, but that's basically how many times it shows up. So if we get the length of that, it's 9. And look how quick that was, by the way. We were able to search the entire text of the entire book, Alice in Wonderland, for the word glass. We know how many times it shows up, and we know where it shows up. That's awesome, right? That's super fast. Imagine a user having that functionality. It's a very powerful thing. Now, to help with our user experience, I create this helpful function. This has nothing to do with the try, by the way. This is just like as a user, I would want to see where the word shows up and sort of like some text before and after to kind of see like the context for that word. So that's basically what I'm doing here. There is an awesome link that I'm providing here for where I got this code from. But basically in Jupyter Notebook, you can print to the screen and have some color. And so here is the color red. And you can also remove color with this. And my window variable is like I want 30 characters before and after the word. That's essentially the idea. But basically I'm passing in the index where the word starts, the word length, because I need to like kind of grab the whole, I want to highlight the whole word essentially. And then I'm putting in also the full text because I need an index on all of that. So all of this functionality is doing that. I'll let you look at the code and this like really wonky F string here. But basically I'm just grabbing all of the instances for where the word shows up and printing them to the screen in a nice colorful way. So let's run this. And so, for example, this is what that might look like. The fourth index, the word is 3 long, and here's the full text. That's the idea. But here, we're going to actually use our try. And here I'm looking for the word queen. And I'm going to see, well, in the entire indices list that we get from this, for each index in there, print the highlight index. We have that index where it starts, the length of the word, which is, 5 for this queen, and then the full text as well. So once we pop that in, we should see a big printout of all the places where the word queen shows up in the text with 30 characters before and after, and the word queen is highlighted so you can kind of get a sense of what's going on. And you can see that it's the queen. It's always the word the right before queen, except here. the king and queen of hearts. Oh, look at that. So here we have all those instances where the word queen shows up in a way that maybe the user would find, useful. It all got powered by a trie. Super quick, super helpful. I love this thing. I hope you love it too. That is it for today, folks. If you enjoy this kind of content, please make sure to like, subscribe, do all the good things, and I'll catch you next time. Take care.